Good morning, everyone, and welcome to the second talk of this cycle of conferences in which, under the title Chemistry, a Hand Outstretched to Society, researchers of our university, who could be considered young in age but not in their scientific career, are going to present different topics related to the chemistry and also including biochemistry too. Only remember, everyone, that the lectures will take place on Thursday at 12:30 always, and will be announced every week in the homepage of Chemistry Faculty, including the link of the registration form. Students who have enrolled for credits for this activity, please let me know by emailing me at the address given in the announcement of this activity. Everyone registered at the seminar will receive an attendance certificate. Today, the turn for this talk is Jose Santos Barahona from Organic Chemistry Department. He will speak about on-surface synthesis of novel polymers. Then I give the turn to the moderator of this talk, David Cecija, of India Nanociencia Institute, who will introduce the speaker and moderate the questions that you can write in the chat. Remember that all your questions have to be written in the Preguntas and Respuestas tab that you have in the bottom of the screen. You can vote the questions you consider interesting, and they will be ordered by the number of votes. Then, David, it's your turn.
Okay, thank you very much, Maria Teresa. Okay, hello everyone. It's a real pleasure today to introduce Dr. Jose Santos. During these years, he has become not only a strong scientific collaborator, but also a close friend. Regarding his scientific background, Jose Santos is an expert in organic synthesis of molecular materials for organic electronics. He's been focused mostly on materials for OLEDs, organic solar cells, and perovskite solar cells. More recently, his interest has also evolved towards the synthesis of precursors for the on-surface synthesis of novel materials. Concerning his academic background, Dr. Jose Santos obtained his Master in Science in Chemistry at the Universidad Complutense de Madrid in 2005. Next, he moved to the Department of Organic Chemistry, where he got a PhD under the supervision of Beatriz Illescas and Nazario Martín in 2010. And there he was researching molecular wires and supramolecular organization of fullerene structures. Subsequently, he moved to a postdoctoral position as research associate at Durham University in the United Kingdom from 2011 to 2014 with Professor Martin Bryce. During this period, his research was devoted to the synthesis of polymers for the fabrication of deep blue OLEDs, along with the development of molecules for thermally activated delayed fluorescence. Later on, in 2014, he moved again back to Madrid as postdoctoral researcher at India Nanoscience in Nazario's Martin Group, and here we met. He has been developing research lines related with molecular electronics with the aim of solar cells and novel devices. In 2015, while keeping his link with India Nanoscience, he also started his academic relation with Universidad Complutense de Madrid with the Organic Chemistry Department. He continued developing his research lines until 2021, when he has become Professor Contratado Doctor at this very same department. He has got a total of 36 scientific articles with over 2,000 citations and a Higgs index of 18. So it's my real pleasure to give you the turn, Jose Santos. We are really expecting your nice talk, and the floor is yours.
All right. Thank you, David. You are being very kind with your introduction. Ahead of all, I would like to thank Maite and the people behind her for organizing this wonderful cycle of webinars where all the researchers from the Complutense have the opportunity to share our research with the community. Well, today's topic is about on-surface chemistry. Well, so what is on-surface chemistry? On-surface chemistry, it's a new topic, a new research area that has arisen quite recently, about 2000, the year 2000 is where you have the first publications about this topic, and consists in, let me show the pointer. It consists in the deposition of organic molecules that are evaporated under high vacuum conditions into a metallic surface. There, under the application of an external stimuli like a thermal annealing or an electronic pulse, you can induce reactions or changes into the molecules, which can be observed by an STM microscope or a non-contact microscope. And you can record them and observe them in a computer. Well, this seems quite simple, but actually it's a quite complex and synergistic area where we need the participations of fields of like organic chemistry. That is my role for synthesizing the precursors by wet chemistry, which is the conventional chemistry, and then we have the role of the surface physicists, like David, which are the guys who deposit the molecules on top of the surface and then analyze them. And finally, in a final step, we have to gather all this information obtained by the microscope, and we have to run some mechanoquantical calculations, normally DFT calculations, so that we predict if the structure that we are seeing corresponds with the reality. So I want to remark that this is quite a highly multidisciplinary field. So it's difficult sometimes to communicate between the partners because we have to know bits of every little field. But the results yield very high yield, very nice research, as I'm going to show you next. Well, how does this work? Well, we deposit the molecules, and as you can see, you can actually observe the molecules. You can see single molecules. This is quite striking because, as most of us studied in our degrees, we thought that single molecules couldn't be isolated molecules couldn't be observed by not naked eye, but you can use a microscope. But we thought that we only could see bundles of molecules, associations of molecules. But now with modern spectroscopies like STM and AFM, you can see here, this is the sketch of a non-contact AFM. This is the tip of the microscope, which has attached a molecule of carbon monoxide. So by tapping on the surface, you can map, and as you can see here, by the scale of colors, you can see that the darker colors means that the deep is very deep. And if you go to brighter ones, you have higher profiles. So in this way, you can see, we observe the molecules with atomistic precision. Moreover, we can just see the structure of the molecule, but also we can characterize the electronic structure by using the STM tunneling microscopy, by applying a bias with a tip on top of the molecules, and we screen all the surface. We can find where the different orbitals are located. So when a given voltage is corresponding with the energy of that orbital, it shines like this bright yellow color. So we can obtain both the HOMO and the LUMO of our molecules. So these two tools, they are very, very powerful resource to both characterizing structurally and electronically molecules. So what does on-surface chemistry differentiate from conventional chemistry? As we know, in conventional chemistry, most of the reactions, they are carried out on a solution medium, where all the reactions occur by collisions between different molecules, and the reaction pathways, they are activated either thermally or photochemically. So in this medium, molecules, they have no restrictions. So you can have some sort of control over the reaction conditions by monitoring the temperature, concentration, solvent polarity, and even more, you can go a little bit further and restrict the free movement of the molecules by the employment of catalysts, which restrict the degrees of freedom of the molecules and allow them to steer them through reaction coordinates that reduce the energy and facilitate the reactions. Well, this is a similar case for the on-surface chemistry. Here, when you have molecules on top of a surface, this surface can be assimilated to a catalyst. So molecules are confined to a two-dimensional space. And here, the degrees of freedom of the molecule, they are highly restricted. So now the molecules can go through reaction pathways that are completely different than the ones from the wet medium. So we can have different outcomes of a simple molecule where you deposit them into a surface. So in considering the nature of the surface, as you can see here, for these two same molecules, depending on whether you deposit them on top of platinum 111 or gold 111, you obtain completely different results. Well, not only the nature of the metal is important, but also the exposed lattice of the metal is quite important. As you can see in this example here, when you deposit these alkynes on top of a silver surface, it's not the same if the silver surface is a 111 lattice or a 110 or 100 lattice. In the first case, what we got is these polymers with this butadiene linker, whereas in the other less compact lattices, what we got is an organometallic polymer where these alkynes are coordinated by these silver adatoms that are taken from the surface. Well, so this reaction here is one of the first examples I'm going to show you of our chemistry. This is been done in collaboration with David here and other groups in Czech Republic. And well, for the first time, we report the synthesis of copper metallocycles from this butadiene precursor with these two anthracene stoppers on the ends of the butadiene. When we deposit them on top of gold and silver surfaces, nothing occurs. You just can see how the molecule, the precursor, tessellates, completely covering the surface. It tessellates it. It's a really nice pattern, but nothing occurs. But when we move to the more reactive copper surface, what we can see here is quite a transformation. You can see these small crosses that they resemble, in my opinion, they look like chromosomes. And if you go into, if we zoom in into them, we can see with the AFM that what resembles a cycle in the middle and the anthracenes in the outside, in the periphery. Well, by running some, we postulate this structure, which was then confirmed by DFT calculations. Always is needed to confirm our proposals by DFT calculation. This is very important. And well, this is the first case of a reported metallocycle of copper like this, when you see a transformation from a butadiene that converts into cumulene. Well, we can also run XPS on the samples, and we confirm the presence of the organocopper linking between copper and carbon by this small shoulder here of the convoluted curve of the XPS. Another example of novel chemistry is this one presented by this Chinese group in 2017, where a dibromovinylene functional group deposited on top of an old surface undergoes the transformation into a cumulene. They have this mixture of cis and trans cumulene. This transformation is counterintuitive with the normal conventional chemistry, where this procedure is more known like the Corey-Fuchs reaction, where when you have this functional group and you dehalogenate the bromines, the molecule by using Uli, what you got is an alkyne rather than the butadiene, sorry, the cumulene. Well, by the same time this article appeared, we were already obtaining similar results, but with a more sophisticated system like this one. Here we also have the dibromovinylene groups here, but also they were linked to a pro-aromatic precursor. In this case, is anthraquinone backbone. Well, when we annihilate the deposited molecules into the surface at 400 Kelvin, what we see is very, very, very long seamless chains, and the structure is compatible with the formation of acetylene links between the different anthracenes, as you can see here, forming long polymers. This was confirmed by the DFT, as I already said. Well, this process undergoes in two different steps. In the first step, you heat the reaction at 400 Kelvin, and you induce the dehalogenation of the molecules. You can see here. Well, sorry. So once the molecules they are dehalogenated, they start diffusing through the surface, and once two molecules collide and find each other, they can form a dimer, as you can see here. Then the dimer continues diffusing until it finds another monomer. Here you can observe a trimer, and if we continue this diffusion and propagation, what we finally obtain is a long polymer. You can see here that in between the chains there are the small dots, the darker ones, they are bromine, atomic bromine in between the chains. And you can see here from the color scale that here I have represented schematically that when you have the dimer, these edges of the molecule or the dimer that they are linked to the surface, the gold surface, they are going down, so they're observed as something dark, whereas these other edges, which are on top, they are brighter. Well, in the second step of this reaction, when we heat up to 500 Kelvin, we induce the desorption of the bromine atoms, and what happens is that what previously was an edge which was linked to the surface, now it detaches from the surface, and it's encapped, or as the physicists say, it becomes passivated by the residual atomic hydrogen that is in the chamber of the microscope. We observe very long chains up to 30 nanometers. We can even go further. I think we can get up to 100 nanometers. They are very robust. They can bend to up to 130 degrees. And they also, I say they are robust because when you apply a manipulation with the tip and move the molecule, the chain, it doesn't break. So they're very robust. Well, we extended this protocol to a longer acene, like the Pentacene, which is a molecule with a very big importance and relevance in the organic electronic field. And we were fascinated and satisfied to observe that what we obtained again were very nice long polymers, as you can see here from the non-contact AFM and the STEM images. But was the structure the same? Well, if you observe these two images here from the anthracene, you can see that in between the anthracene units, we have a bright spot, whereas in the Pentacene one, we don't have this bright spot. This bright spot is, let's say, the firm or the feature, the characteristic feature of triple bonds. You know that triple bonds, they have cylindrical geometry. So when you go with the microscope, with the EFM tapping, you and you find the triple bond, so you have to go up. So it seems brighter like this, which is not the case for the pentacene, where there is no bright spot. So we confirm this by DFT calculations. You can see here that you have very short triple bond here of 1.21, whereas for the case of the pentacene, this what should be a triple bond is now longer, but what should be a single bond is shorter. And also the structure of the pentacene is less aromatic and more resembling a quinoid structure. So what we have in this case of anthracene is aromatic and triple bond, and in the case of pentacene is quinoid and cumulinic. Well, we extended this also to the family of the periacenes, which are acenes that are linked through their peripositions. And in this case, this is Byzantine, which is obtained from this biantron precursor. And again, we have this really beautiful image of our molecules. Is fantastic, the resolution which you can observe here, the atoms, the single atoms. Well, by STS, scanning tunneling spectroscopy, we can calculate, we don't calculate, we measure the band gap of the molecules. And for the case of the aromatic anthracene, this band gap is the low band gap of 1.5 electron volts. Whereas in the case of the quinoid structures, like the pentacene polymers and the Byzantine ones, we have these strikingly low band gaps of 0.35 electron volts and 0.30. This is striking because this is, we can say that it's quasi-metallic. This is almost metallic, taking into consideration that the what is called conducting polymers that are employed nowadays, they have in organic electronics, they have band gaps that they are around this value, 1.5, 1.3 electron volts. So this can be considered almost metallic. So what's going on here? Why larger acenes are becoming quinoid? Well, if we focus into the frontier orbitals of the systems, you can see that for the aromatic anthracene ones, what is the HOMO? It resembles what we can say a bow tie or pajarita in Spanish. Here is the HOMO, and in the case of the pentacene, this bow tie orbital appears on the LUMO instead of in the LUMO, and in the case of the LUMO occurs the same. These bright spots, which are the LUMO of the anthracene, become the HOMO of the pentacene. So what we got here is an orbital inversion. Well, this resembles trivial, doesn't it? Well, actually, it is not. And now I'm going to briefly and very shallowly explain a bit of the topological theory, which is a branch of the physics, which is quite in the fringe of the research. So this studies the electronic structure of the molecules. So by applying this transformation here, which is the SAC transform, we apply that to the bands of the molecules, and we can know whether the molecules, they are considered topologically trivial or non-trivial. They are trivial when this invariant equals 0, whereas when it equals 1, it's non-trivial. As you can see here, when we calculate from the phenylene polymer, anthracene polymer, they are trivial, which is the normal molecules with the structure, the normal structure, electronic structure we are used to. And in the case of the pentacene and hyracenes, we are in the non-trivial range. So what does this actually mean? So these two phases, they are separated by a phase transition. So in this boundary, as the Suess-Schrieffer-Higge model, when you go from one phase or the other, we must pass through a zero gap state. So zero gap means this, that the gap between the HOMO and the LUMO becomes zero, which is the case in our case, is the case of the Pentacene one. Then as we go further into the non-trivial range, well, this gap starts to slowly broaden again. In chemical terms, this translates as the level crossing I showed you in the previous slides, where the LUMO of the trivial one becomes the HOMO on the non-trivial, and the HOMO of the trivial becomes the LUMO of the non-trivial. Well, another interesting feature of these non-trivial electronic structures is the appearance of what is called edge states. These edge states, they are characterized to appear in the middle of the Fermi band here at zero bias, and they normally they always appear at the edges of the molecule, not in the bulk of the molecule. So when you go to the very end of the molecule, what you see is the appearance of these states, which are showed here, both in the STM and also in this plot here. This these edge states, they are interesting from the topological point of view because they are topologically protected. I'm not pretty sure about what this means. I am quite sure that most of the physicists researching this, they are not sure as well, but has been something in the fringe of the research. We are really interested in experimenting with them so we can know what properties they have, because we feel that they may have very important applications in the fields like quantum computing and information transfer. In a further development of these experiments, we observed previously that some of the molecules of the Pentacene polymers, they were shorter than the larger ones, and the shorter ones, they weren't non-trivial. So we decided to run an experiment and taking long polymers and hydrogenating them by introducing atomic hydrogen into the microscope chamber. As you can see here, it randomly hydrogenates. As you can see, the hydrogenation is denoted by these brighter spots here, because they are bright, because they are no longer planar, so they are no coplanar with the surface, but they are protruding up to us, let's say, in the Z axis. Then, by the application of a bias with the tip of the microscope on top of these hydrogens, we can selectively dehydrogenate them, and we can at will, we can engineer these long hydrogenated chains. We can engineer them by at will building segments of different lengths. So we prepare this segment, which is short, and this one, which is quite long. And then we can measure by STM the orbitals, and we can see that for the longer ones, once again, they become non-trivial, whereas the short ones, they are trivial. So you can see in the non-trivial ones, you see the edge states, and also interestingly, you can see the frontal orbitals inversion. You can see here how the LUMO of the trivial becomes the HOMO of the non-trivial, and the very famous bow tie, which is the HOMO of the trivial, becomes the LUMO of the non-trivial. Well, by plotting the different sizes of chains, we can find that the limit for the non-trivial range, it lies on the n equals 25 monomer. So once we transition from 24 to 26, we are starting to be in the range of the non-trivial structure polymers. I think this is probably the first time that this sort of experiment is being carried out, and these are probably the first non-trivial polymers ever found on a surface. Well, a further transformation that can be observed in these polymers is that when you overheat them at 650 kelvins, we observe another reaction, which is also new. Here you can see that the cumulene linker between the bisanthenes transforms into pentylene linker. Again, you can see how neat the images are. You can discern perfectly every atom, every single ring of the system. And how do we explain this transformation? This is quite interesting because we compare this with anthracene, and we try to do the same, and nothing happened. Whereas in the case of the Pentacene, we also have this similar results as this one. So how could we explain that for one or the for the longer ones, the reaction works, and for the anthracene, the aromatic ones, it doesn't? Well, for that, we run calculations for the vibrational modes of the system. And as you can see here, the red arrows are the vibrational modes, and the blue arrows are the reaction coordinates. And for the case of the bisanthene, you can see that the modes, the vibrational modes, they almost overlap with the reaction coordinates, whereas in the case of the anthracene, these modes, they don't overlap. And this is the other explanation of why these aromatic polymers, they cannot polymerize, not polymerize, they cannot undergo this transformation into forming the pentylene linkers. Well, we confirm that the aromatic structure is the one showing you here in the bottom of this part of the slide, which the one showing the maximized number of class sextet. For the ones you don't know what a class sextet is, a class sextet is this one. It's a phenyl ring with 3 equal resonating double bonds. We can confirm also by next calculations that the bisanthene has aromatic structure, and also that the pentylene is strong, very strongly non-aromatic and anti-aromatic, sorry. Also, we can calculate the band gap, which is around 1.1 volts. Well, and finally, as a summary, I have to say that we have developed a very powerful methodology to obtain polymers of acenes and periacenes, starting from very cheap precursors on top of the surface. These polymers we have shown are probably I'm quite sure that they are the first one-dimensional polymers that have that show a non-trivial topology. We also have demonstrated that we are able to engineer polymers that have alternating segments of either trivial and non-trivial topology, which is something interesting, which might have at some point a certain application. And most importantly, is that we have foreseen a strategy for achieving metallic or quasi-metallic polymers by approaching to the topological phase transition, as is the case of the Pentacene molecule. Well, this is all. Now I acknowledge our collaborators. First of all, Eider Rodriguez, which is a student, the PhD student, also Nazario, which is our IP, and in the group of David Cecija from Indiana Nanociencia. These are his PhDs and also postdocs. Our collaborators in Czech Republic, Pavel Jelinek, Radek Boril, collaborators in EMPA in Switzerland, Oliver Gronin, and several others. Well, thank you very much. This is all.
Okay, thank you very much, Jose, for this very nice introduction. And now I think, Maria Teresa, it's time for the questions.
Yes, I mean, you can, I don't know if you have any question in the chat.
Yeah,
no.
I think in the chat I didn't receive any. But
Then,
please don't be shy, the listeners, if you have any question. If not, probably I can start Jose directly with a few questions, and then we wait for the shy audience to join in with questions. Okay, so then my first question, of course, since given your expertise about organic chemistry, I would like you to comment more on the complex procedure or the complexity of really synthesizing these molecular precursors. What were the problems you really encountered during the synthesis, and what can be achieved and cannot achieve?
Well, at the very beginning, the reaction seems quite simple because it's, let me find where it's it. You can see here, we follow this Ramirez-Corey-Fuchs protocol. We start from a ketone, and by employing tetrabromo-carbon with triphenyl phosphine, we obtain this dibromovinylene moieties. At first, with the first quinones, the reaction was really easy, but as we try to go for more complicated structures, we have to struggle with the conditions. At first, we weren't able to succeed into getting more complex systems. We shifted the conditions towards employment of different phosphines. Then we turned to phosphides, and even we tried with some kind of halides of carbon phosphine halides. Well, it's a bit messy sometimes for the more complex structures that our collaborators asked us, but I think we're doing it quite well.
Yeah, sure. Okay, now people are joining, so just a few questions. So Bagrat Abramian is asking the following question. Do you believe it would be viable to increase the length of these polymers by a level of magnitude? So essentially he is asking if you could really synthesize longer polymers.
Longer polymers. Well, as far as I know, our polymers, they are already about, correct me if I'm wrong, David, because you're also quite familiarized, around 100 nanometers, which is quite long. I think the main limitation is that the termination of our polymers start when certain atoms of hydrogen that they are always present in the top of the metal, they find one of the ends of our polymer, propagating polymer, and then they passivate, they detach it from the surface, and they passivate. So perhaps if we try to completely remove the hydrogen, we may get very, very extremely long polymers, but I am not so sure you can completely remove the hydrogen.
Okay, thank you. So next question is from Fatima Garcia. So she's asking, do you think you can shift from the quinoid to the aromatic resonant form for the same substrate by changing the surface? I think, okay, so probably if I understood correctly, she's asking if using just the same metal, just by using another phase, yes, you could change the resonant form.
I know that we are currently carrying out that research. I am not sure, but what I want to stress out is that this electronic structure, yes, it's an electronic structure, doesn't depend on, where was this? Sorry. Doesn't depend on the substrate, but on the calculation run by the Sacking invariant. So we apply this transformation into the bands of the polymer, and it depends on the result, whether it's 0 or 1. This is not depending on the substrate. It only depends on the band structure of the molecules.
Okay, then
as far as we are aware.
Then let's go to the, okay, that is a general question. I mean, this is from fundamental chemistry, but probably you could comment also. What is the meaning of anti-aromatic?
Anti-aromatic. Anti-aromatic, well, when you must, well, all degree students should know that, chemistry degree students should know that an aromatic structure must accomplish with the Hückel rule. So when you have 2n+2 electrons, you are aromatic, and when you are when you don't have this, you are anti-aromatic. Which are the consequences when you have something aromatic? The molecule, the structure is quite stable, as you can know, as you will know from benzene. It's a very stable aromatic compound. But when you have anti-aromatic molecules, these anti-aromatic molecules, they are very unstable. Some of them, they are even radicalic, so they are quite reactive.
Okay. Thank you. So this question was from Seviku. I don't know. It was a short name. So then I think we don't have further questions. But then probably I would like to ask you a couple more. So next question is: you know all the experiments, all these experiments have been done on a metal, and what do you envision it could happen on an insulator, for instance, or on something which is not a metal?
I don't know. It's a good question. I am not so sure, because we know that the metal has a strong influence in forcing the molecule to undergo the reaction. I don't know. Probably, I mean, there are examples of reactions going on insulators, but I don't know if the reaction coordinate will follow the same path and reach the same products. It's something to be studied. What is clear is that if you have an insulator, I guess that the electronic influence of the metal, the shielding of the sea of electrons that a metal is, won't be the same in an insulator. So probably you can measure different things, and also the gaps may vary a little bit.
Okay, thank you. And my very last question is, of course, these materials have been done in ultra high vacuum conditions on a pristine monocrystal. So then the question is, how do you envision, or could you comment on the prospects of really extracting this chemistry to the real chemistry? So really going outside from ultra high vacuum to liquid environment or directly to air. What do you envision? What are your thoughts about this?
I find that it's quite tricky question, because yes, obviously the best outcome would be to do it in non-vacuum conditions, but consider that when you have a molecule on top of a metal, this is something really reactive, and if you have the presence of any other contaminants, let's say oxygen, whatever gas, whatever contaminant in the atmosphere, you are activating as well the reactivity. So I am not pretty sure you can completely go for non-vacuum conditions. What I envision is that obviously what we are using here is very tiny samples of metal. So the number of molecules you can deposit in a very tiny monolayer of a metal is ridiculous, we can say. It's not about milligrams or neither micrograms, probably. So with the aim to go for industrial purposes, probably we will need to develop processes, probably less vacuum, and instead of using small crucibles, well, not crucibles, sorry, metal crystals, probably long shields of long leaves of metal, foil it. I don't know. Probably that's the way to proceed.
Okay, thank you, Jose. I think we don't have further questions, but we have a comment from Professor Nazario Martin. So he's telling that the nature of the reactive intermediate formed by heating from the dibromovinylines could give the answer to this question. I mean, on the deposition on non-metal surfaces. Yes, I mean, thank you, Nazario, for the comment. And yeah, so let's see if anyone more joins in. If not, I think I'm fine with this. You know, we chat every day, Jose. So
yeah, sure.
So it's pretty fine. So just see if the others.
Very exciting research.
So just to summarize, this was a very exciting talk about a real. We have. Okay, that I was asking. So I think just for summarize to the community, this was an excellent thought about a really emerging field in chemistry regarding on surface synthesis of potentially useful materials. And it's been great, Jose. So thank you very much. And now I give the turn now to Maria Teresa. Thank you.
Okay, thank you very much, Jose. Well, I had several questions, but always because I am a biochemistry, then sometimes it's difficult to ask questions with serious questions, and for me, I have only one. You are always speaking about homopolymers, no?
Yes.
Always,
yes.
Because. Well, I think that if I am biochemistry, then I think always in enzymatic catalysis, the enzymes are also a surface in which you can have different catalysis, and also you can polymerize some materials. And my question was this: I mean, if you in the future this kind of technique can polymerize heteropolymers.
You mean by heteropolymers? You mean with different monomers, no?
Yeah,
Copolymers.
of different monomers. Yeah.
Yes, sure. I mean, I think we have already tried. We haven't published this yet. I mean, in this case, they are. This is a copolymer. Obviously, it's not a homopolymer. It's a copolymer of anthracene and acetylene, but we could use different mixing different monomers. For instance, we can use an anthracene monomer with a pentacene one, and then we will have what we will have is a random polymer, because we can.
Yeah, because you cannot control the stoichiometry.
Right.
No?
That's right.
Okay.
But well, probably there will be. I mean, you can apply different strategies as the ones employed in polymers chemistry, like trying to link, let's say, an anthracene to a pentacene and then polymerize. But again, it will be random as well.
Okay. Well, thank you, Jose. It was a nice talk. I thank a lot, and David also to moderate the talk. And I tell everybody that the next talk is October 7th. The title is Journey Inside the Body, How to Study Cardiovascular Diseases Using Magnetic Resonance Imaging. And you have the link for the registration in the chat of this talk. Okay, thank you very much, everybody. And see you next Thursday.
It was my pleasure.
Okay.
It was my pleasure. Bye-bye. Have a good day. Ciao.